Welcome to a lesson with Dr. Powell. Let's talk about how we can get asymptotic inequalities um, with, with actually just looking at limits. Now, for instance, this is pretty clear just generally that since n cubed is bigger than n squared, and then we're putting them in denominators, so flipping the sign or flipping the direction of the inequality, we have 1 over something bigger is smaller than 1 over something smaller, right? So now in general, we could see this idea a couple of different ways. What if we took this guy and we put it over that guy and thought of this fraction? In particular, let's think of what happens to this fraction asymptotically as n goes to infinity. Now, let's see, we can rearrange, we can multiply top and bottom by n cubed. And this looks like the limit as n approaches infinity of 1 over n after simplifying, which is clearly 0. This means that this is eventually behaving like 0 compared to this, which means that this eventually is smaller than that. So when you take a ratio of two things and get 0 eventually, that means that one thing definitely is going to be smaller than the other thing eventually. You've just established an asymptotic inequality via a limit. If you just take a limit of ratios and then go for it, sometimes L'Hopital's rule might be handy. Let's see now, what if we did the opposite ratio, 1 over n squared? So take this guy over that. And now as we simplify this, so this will have the same limit as n. So this is actually, if we multiply top and bottom by n cubed, we'll get n, and that goes to infinity, which means that this limit goes to infinity so that the top is eventually a whole lot bigger than the bottom. So we've established the inequality based upon our interpretation of the outcome of the limit. Now, what about something like this? Notice this funny notation I use. This is asymptotic equivalence. So this asymptotic equivalence, that simply means that we could have an asymptotic inequality going either way, just depending on changing the constant. So for instance, n plus 2, right? If we want the inequality to go this way, then the denominator, we want something smaller than n plus 2. So we just pick n. So just automatically, this actually is just like that right now. Now, if we want the inequality to go the other way asymptotically, then we think we want, okay, so we want this happening. Then it's reverse. So we want n plus 2 smaller than something. And what would be smaller than? It'd be smaller than double the leading term, so 2n. So we'd have something like this. So in other words, the inequality could work either way by attaching a different constant on one side or the other, and you could get that. That's what this means. This means that you could get an inequality either way, just having to change the constant. Now, one way of seeing that you can get an inequality either way is if when you take a limit of the ratios, you end up getting a constant, meaning that eventually, and think about what that means. So let's see, 1 over n and 1 over n plus 1 and 2. This changes to rearrange to n plus 2 over n. You take a limit with L'Hopital's rule, you end up getting 1, which means eventually n plus 2 is within a small amount of n away from n, or n is a small in this ratio here, or what I mean is 1 over n is within a small amount of 1 over n plus 2, okay, as we take this limit. So these guys are close to each other is what I was trying to say, as we take this limit at if it's equal to 1. If it's equal to k, that means eventually one thing is like k times the other thing, more like, and if it's close to it, it could be close, a little bit bigger, a little bit smaller, but we could modify k, the constant, make it smaller or bigger, to change the inequality around. But the main idea is that if you take a limit of two things and you end up getting a constant number, that means the convergence divergence of one will be the exact same as the convergence divergence of the other. Now, if you get zeros and infinities, then that just means that one is smaller, one is bigger, then you can determine convergence divergence that way, perhaps. But this is also useful as well. So we can use those ideas as we move along. Thanks for watching.